Hi, in this lecture, we will study the meaning of asymptotic performance of algorithms and how to use asymptotic notations to formally compare the performance of algorithms. Furthermore, we'll be looking at some important properties of such functions and many other functions that will be needed in the analysis of algorithms throughout this book. This lecture covers Chapter 3 of your textbook. Before we proceed, let us recap what we know so far. In Lecture 1, we introduced the concept of order of growth as a feature to characterize and compare the performance of algorithms. We studied two sorting algorithms and compared them in terms of their worst-case running time. We saw that for a large input size, the merge sort asymptotically outperforms the insertion sort as it has a logarithmic factoring. So I briefly gave you an idea about the concept of asymptotics, which was forgetting about the constants and concentrating on the leading terms in determining the worst-case running time of algorithms. However, that was just an informal definition. We will be looking at a more formal or mathematical definition of various asymptotic notations in this lecture. Keep in mind that the asymptotic notations that we will see in here are applied only to functions. That is, for example, we saw that the worst-case running time for insertion sort is a quadratic function of the input size n, which we denoted by theta n squared. Similarly, for the merge sort, we obtained the recurrence equation and found its worst-case running time to be theta of n log n using the recurrence tree. However, I did not tell you what theta means and whether it can be used to characterize all types of running times or just the worst-case running time. To understand this, let's now formally define the asymptotic theta notation. So, the theta notation, also known as the asymptotic tight bound, is defined as below. Let g of n be some function. Then theta of g of n denotes a set of functions such that for every function f of n in this set, there exists some positive constants c1, c2, and n0, such that f of n is bounded by c1 times gn from below and c2 times gn from above for all values of n greater than or equal to n0. In other words, f of n is sandwiched between c1 times gn and c2 times gn. As we see that theta g of n is defined as a set of functions, so we could basically just write f of n belongs to such a set. But instead we use the equal sign. This equal sign doesn't have the same meaning as we see in algebra, but it is a replacement for belongs to. And why we use it? Because it's more convenient, and we will see why in future. We therefore say that G of n is an asymptotically tight bound for f of n, as it bounds f of n within some constants c1 and c2. Also note that we are only interested in the asymptotic behavior that happens in the first quadrant of the xy axis. And this is given in the definition over here. So we are only interested in the non-negative values of n for which there is a minimum bound which should be non-negative. Therefore, as n grows or increases, there exists some n naught value after which f of n will always be some function between these two bounds. Before n naught, that may not be the case. So we are looking at the asymptotic behavior for every n value that is greater than n naught. In the previous lecture, I gave you an informal definition for theta. I told you that once you have the running time function, throw away the lower order terms and ignore the coefficient of the dominating term. Now let's try to justify this informal definition using the formal definition that we just saw in the form of an example. In this example, we have g of n, which is equal to n squared. Therefore, theta g of n is the asymptotic tight bound of function f of n. Based on the definition of theta, we now have to find some positive constants c1, c2, and n0 such that these inequalities are all satisfied. To do so, we first divide this whole inequality by n square. That means if we divide it by n square, we get this. Now, we have to plug in values of n which are positive integers such that this would be some positive value. Let's begin with n is equal to 1. For n is equal to 1, we would get this, which when simplified gives us minus 5 divided by 2. Therefore, C1 cannot satisfy this condition, and therefore this is wrong. Then we go to n is equal to 2. Similarly, we get minus 1, which is negative, and therefore it is not correct. We keep doing this until we reach n is equal to 7. Over here, we see that we get 1 divided by 14, which is positive, and therefore satisfies the positive requirement of C1 and C2. Therefore, this verifies that f of n is equal to theta n squared. In another example, now let us use the formal definition of theta to verify that 6n cubed is not equal to theta n squared. To do so, we use proof by contradiction. So we assume that there exist some positive values c1, c2, and n0 such that the definition for theta notation holds. Let us pay attention to this part of the definition. By dividing this part by n squared, we would get n is less than equal to c2 divided by 6, where c2 is some positive value. But we know that n cannot be bounded from above because n can be any sufficiently large value. So this implies that our assumption was wrong, and therefore 6n cubed cannot be equal to theta n squared. As an exercise, I request all students to take a look at this problem and try to prove the same using the definition of theta. A hint is given over here. The next asymptotic notation is the big O notation, also known as the asymptotic upper bound. So far, we have seen that the theta notation asymptotically bounds the function f of n from up and down. But what if we are only interested in the asymptotic upper bound? In that case, we use the big O notation. So the formal definition of big O notation is given as such. For a given function g of n, big O g of n is a set of functions such that there exists f of n function where for positive constants c and n naught, we have this condition that is satisfied. Therefore, if we look at this example, we see that for the quadratic function f of n is equal to a n squared plus bn plus c, where a is positive, f of n is equal to theta n squared, which is true, and f of n is also equal to big O n squared, which is also true because it is upper bounded by n squared. So we note that f of n is equal to theta g of n implies that f of n is actually also equal to big O g of n, since the theta notation is a stronger notation than the O notation. Therefore, the theta g of n would be a subset of big O g of n. The graphical representation of the big O notation can be seen over here. So beyond any n naught value, for every function f of n that lies below the g of n function, we can say that f of n is bounded from above by g of n. Therefore, f of n belongs to the set big O g of n. Some simple examples are also given over here. For example, 2n squared is equal to big O n cubed, which is true because n cubed has a higher order as compared to n squared. 2n squared is also equal to big O of n squared because n squared is bounded by n square itself. In the third example, we see that the leading term has n times log n, which is an element in the set big O n square, because log n grows at a lower rate as compared to n. As an exercise, I ask you to try to prove this problem using the definition of big O notation. A hint is provided over here. In contrast to the big O notation, omega notation, or the asymptotic lower bound notation, actually gives us a lower bound of any given function f of n. As we see in this figure, for any n value greater than n naught, all f of n functions that are above the g of n function actually belong to the set omega g of n. So the formal definition is the set of any f of n functions such that there exists some constants c and n naught that satisfy this condition. As examples, 2n square actually is an element in omega n square and also an element in omega n, because 2n square has an order of growth equal to n square and greater than n. Similarly, n log n also is equal to omega log n, because n log n grows at a higher rate as compared to log n. Now that we know the definitions for theta, big O, and omega, there exists a very interesting theorem. It states that for any two functions f of n and g of n, we have f of n is equal to theta of g of n if and only if f of n belongs to big O g of n and f of n belongs to omega g of n. The proof is quite simple and straightforward. From the definition of big O notation, we actually have this. From the definition of omega, we have this. Since it is an AND operation, we can conclude that there exists some C prime and C double prime and N naught that are positive and that satisfy this condition. Keep in mind that the N naught that we define in the AND operation is actually the maximum of N naught prime and N naught double prime. Sometimes you may come across an expression as shown over here, where you have a asymptotic notation on the right-hand side. So what does it mean? This tells me that there exists some anonymous function that we do not care about, which in this case is equal to 3n plus 1, because as n grows sufficiently large, this anonymous function has no impact on the order of growth. That means, to formally express this, I would say that there exists some f of n, where this f of n is a function that belongs to the set theta n. We have already seen that the best case running time of the insertion sort is a linear function of the input size n. Therefore, we can say that the best performance is achieved when the input array is already sorted. Since omega n gives a lower bound, it is correct to say that the best case running time is omega n. So the insertion sort has a running time of omega n as it is bounded from below and big O n square as it is bounded from above. Can we also say that its running time belongs to omega log n? Yes, because the order of growth of log n is less than n, which is the best case for the insertion sort. How about big O of n cube? Yes, because n cube grows at a higher rate as compared to n square, which is the quadratic function of n and is the worst case running time for insertion sort. However, we cannot say that the running time of the insertion sort belongs to omega n square, because there exists some input for which this algorithm runs in theta n, and that is when the input is already sorted. Also, we cannot say that the worst case running time of the insertion sort is omega of n square, because there exists some input for which it actually causes the algorithm to take n square amount of time and some input that causes the algorithm to take n amount of time. The asymptotic notations that appear in equations or expressions are considered as anonymous functions that abstract the details of the lower order terms. For example, this summation expression contains one anonymous function, which is a function of I, and it is not the same as saying big O of 1 plus big O of 2 until big O of n, as it cannot be interpreted logically. In some cases, the asymptotic notation may also appear on the left-hand side of the equation. This is an example of such a situation, where the right-hand side is less informative as compared to the left-hand side. So what this tells us is, it means that for any function f of n that belongs to theta n, there exists some function g of n that belongs to theta of n squared, such that 2n squared plus f of n is equal to g of n for all n values. The next asymptotic notation that we will be studying is the small o notation, which is actually the asymptotic loose upper bound. We have seen that the asymptotic upper bound provided by the big O notation means that it may or may not be asymptotically tight. For example, we can say that 2n squared is bounded by big O n squared, or we can say that this equal to is actually less than equal to big O n squared. So it is asymptotically tight. But we cannot say that 2n is less than equal to big O n squared, because the equal condition does not satisfy. So the small o notation is used to denote the upper bound that is not asymptotically tight. The formal definition is given over here. For a given function g of n, small o g of n is a set of all functions such that for every f of n in this set, there exists some constant c value and there exists some constant n naught value such that this condition is satisfied. So the difference between the small o notation and the big O notation lies over here. In the big O notation, we have an equal condition as well, while in the small o notation, it is strictly less than. As an example, we have 2n is equal to small o n squared. So 2n is f of n, and n squared is g of n. So this is true. But we cannot say that 2n squared is equal to small o of n squared, because this does not satisfy. The equal sign doesn't satisfy, right? So the main difference between the definition of big O notation and small o notation is that in f of n equal to big O of g of n, f of n is bounded from above by cg of n, where this condition holds for some constant values of c. But in the case of small o notation, this bound holds for all conditions of c. So if you take the relation between f of n and g of n, and you take the limit as n approaches to infinity, we would see that this limit goes to 0. It means that the function f of n becomes relatively very insignificant as compared to g of n for sufficiently large values of n. Just as the definition for the small o notation, which was an upper bound that is not asymptotically tight, we have a definition for a lower bound that is not asymptotically tight and corresponds to the big omega notation. This is the small omega notation. And the formal definition is as such. For a given function g of n, small omega of g of n is a set of functions such that for every f of n in that set, there exists some constant c greater than 0 and some constant n not greater than 0, such that this condition is satisfied. So again, we are emphasizing on this. So note that f of n is small omega g of n if and only if g of n is small o of f of n. This is a very important property. Let's look at an example. N squared divided by 2 belongs to the set small omega of n. Yes, because it has a higher order as compared to n. Therefore, this is greater than this. But n squared divided by 2 is not equal to small omega n square, because n squared divided by 2 is not greater than n squared. So if we take the limit of f of n and g of n as n tends to infinity, we see that f of n grows significantly larger as compared to g of n, and therefore this limit would go to infinity. Interestingly, the relational properties that we have seen in real numbers also apply to asymptotic notations. So if we assume that f of n and g of n are asymptotically positive, that means their values are always positive for sufficiently large numbers, then these properties hold for them as well. The first one is transitivity, and it says that if f of n is equal to some theta of g of n and g of n is equal to some theta of h of n, then this implies that f of n is equal to theta of h of n. This is the same as saying if a is equal to b and b is equal to c, then this implies that a is also equal to c. So this holds for all types of notations that we have seen so far. The next one is reflexivity, and it says that f of n is equal to theta of f of n is equal to big O of f of n and is equal to big omega of f of n. This does not hold for the small notations small o and small omega. We then have the symmetry property, which states that f of n is equal to theta of g of n if and only if g of n is equal to theta f of n, which is quite obvious. Then we have transpose symmetry, which is the same for big O and small o notations with respect to big omega and small omega notations. So if we want to draw an analogy between the asymptotic comparisons and the comparison between two real numbers, say a and b, this is how it would look like. So the big O notation basically means less than equal to. The big omega notation basically means greater than equal to. The theta notation is actually only equal to. Remember, we do not have small theta because it would make no sense. The small o notation basically corresponds to strictly less than, and small omega means strictly greater than. So we can define asymptotically smaller or larger functions by using the small o and small omega notations. For example, we can say that a function f of n is asymptotically smaller than some function g of n if f of n belongs to the set small o of g of n. That means as n tends to infinity, the limit of the ratio of f of n and g of n would go to 0. And that's because f of n would grow at a much slower rate as compared to g of n. Similarly, we have the definition for asymptotically larger, where f of n would have a higher or faster growth as compared to g of n if we take their limit and n tends to infinity. However, there is one property of real numbers that does not work in asymptotic notations, and that is trichotomy. It says that for any two real numbers a and b, exactly one of these conditions would hold. Either a would be less than b, a would be equal to b, or a would be greater than b. But this does not always make sense when it comes to comparing asymptotic notations. That means not all functions can be asymptotically comparable. Take a look at this example, where we want to compare functions f of n is equal to n and g of n is equal to n to the power 1 plus sine n. If we look carefully, we observe that the exponent of g of n, that is 1 plus sine n, oscillates between 0 and 2, as sine n can have a minimum value of -1 and maximum value of 1. So this would look something like this. So we see over here, the red line, which denotes f of n, cannot be compared asymptotically with the blue line, which corresponds to g of n, as g of n moves up and down around the line f of n. With that said, now let's take a look at some standard functions and their properties that we are already familiar with. The first one is a monotonic function. So a function f of n is said to be monotonically increasing if m less than equal to n implies that f of m less than equal to f of n. Similarly, we have a monotonically decreasing function if for m less than equal to n, f of m is greater than or equal to f of n. So this can be made more strict by defining strictly increasing or strictly decreasing function by removing the equal sign over here. We all know how the floor and ceiling functions work. To quickly refresh our memories, let us look at some of their important properties over here. In the first property, we see that the floor of x is some value that lies between x minus 1 and x, including x. Similarly, the ceiling of x is a value between x and x plus 1, including x. We also know that the ceiling of n divided by 2 plus the floor of n divided by 2 will always be equal to n. This is a property that we use in our merge sort. Similarly, we have this property, which is very straightforward. And looking at this graph, we see that the functions floor and ceiling are actually monotonically increasing in both cases. The modular arithmetic is given as a mod n, where a mod n actually is the residue of the coefficient a divided by n. So a mod n is equivalent to a minus n times the floor of a divided by n. You can quickly plug in some values and check that this actually is true. So we can always say that a mod n will always be a value from 0 to n minus 1. We can also say that if a mod n is equal to b mod n, where a and b, for example, can be 3 and 5, and n is equal to 2. So if we have 3 mod 2 is equal to 5 mod 2, which is true because both of them give us the result 1, then we can write it as this, where it is read as a is equivalent to b modulo n. So we can define a polynomial as the sum of the product of ai's and n to the power I for some non-negative integer I. So P of n would be of the form summation I from 0 to d of ai times ni, where ai are coefficients and ni's are the polynomial terms. So we can say a function f of n is polynomially bounded if f of n has an upper bound defined by big O n k. For example, if f of n is equal to n square, then we can say that n square is polynomially bounded by big O n square, or big O n cube, or big O n to the power 5. We all know all about exponentials and their properties. So for any real value a greater than 0, m and n, we know that all these properties hold. If we want to relate the order of growth of polynomials, that means n to the power b, and exponentials, that is a to the power n, what we need to do is take the limit as n tends to infinity. And we see that this limit tends to 0. So this tells us that n to the power b, that means the polynomial is an element in the set small o a to the power n. In other words, the order of growth of the polynomial is insignificant as compared to the order of growth of the exponential function as n becomes sufficiently large. On this slide, we have the definition for the logarithmic function. What you should keep in mind over here is the difference between the different notations. When we use Lg of n, we mean the log to the base 2, which is called the binary logarithm. If we use Ln of n, we mean the base exponential. Lg to the power kn is the same as writing Lg of n whole power k. And finally, Lg of n is actually the log of log n. This is known as composition. Now, if a, b, and c are real numbers greater than 0 and b is not equal to 1, we know that these properties hold, and you have seen this earlier in high school. Question: under what condition would the function log base b of n be strictly increasing? I will give you the answer, but I want you to think about it later. When b is greater than 1 and n is positive. We can say that the function f of n is polylogarithmically bounded if f of n belongs to the set big O of log to the power kn for some constant k. We know what factorials are. So given any non-negative value for n, we have this definition. N factorial will be 1 if n is equal to 0, and would be n times n minus 1 factorial, which is recursive if n is greater than 0. So we can define a weak upper bound on the factorial n factorial given as such. So n factorial will always be less than or equal to n to the power n, since there are at most n number of terms in the product of the factorial. Another interesting property is the Stirling's approximation. I do not expect you to know how to derive this, but we will be using this equation to solve some problems in future. Note that we have an asymptotic notation on the right-hand side of the equation. Finally, we will be looking at the definition of Fibonacci numbers. A Fibonacci number is the sum of two previous numbers in a given sequence. So if we begin with 0 and 1, the next number, which is 1, is obtained by adding 0 and 1. The next number 2 is then obtained using 1 and 1. 3 is obtained by adding 1 and 2, and so forth. So if we want to write this down recursively, this is how it would look. Given that f of 0 is 0 and f of 1 is 1, f of I would be f of I minus 1 plus f of I minus 2 for any I value greater than equal to 2. Another way to calculate the Fibonacci number is using the golden ratio, denoted by phi. This is the equation for it. So we can find the ith Fibonacci number in a Fibonacci sequence by using the term phi and phi hat, which are actually conjugate values and are obtained as here. So if we plot the Fibonacci numbers in a Fibonacci sequence, we would see that they grow exponentially. A very interesting video on golden ratio and its application in different disciplines can be seen in this link.